Welcome back to our deep dive series exploring the really fascinating corners of the OEIS.
It's always a pleasure. So much hidden structure in numbers.
Absolutely. Today we're zoning in on one sequence that's particularly interesting for number theory students. It's A000189.
Ah, yes, a good one.
And the description is number of solutions to x cubed congruent to 0 mod n.
That's right. So for any whole number n you pick, we're just counting how many numbers x between 0 and n minus 1.
So in that specific range.
Exactly. How many of those, when you cube them, give you something that's divisible by n, or congruent to 0 mod n?
Okay, and our mission today basically is to figure out what this sequence, what counting these solutions tells us about, well, cubes modulo n?
Precisely. It sounds simple, maybe, but it opens up quite a bit about modular arithmetic.
Right, so let's look at the first few terms. It starts 1, 1, 1, 2, 1, 1, 4, 3, 1, 1, 2. Quite a mix there.
It does jump around a bit, doesn't it? Then 1, 1, 1, 4, 1, 3, 1, 2.
And the OEIS entry mentions the offset is 1, 4. What's the significance of that?
Well, the 1 tells us the first term listed, that 1 corresponds to n1, so A1, 1.
Which makes sense. X0 is the only solution for by 3 congruent to 0 mod 1.
Exactly. The 4 bodicoming in the offset sometimes points to maybe an older starting point or a version, or just highlights a particularly interesting early value. In this case, A42 is maybe the first non-trivial value.
Okay, and there's this comment too. Shadow transform of the cubes, A000578. Now, A000578 is just the sequence of cubes, 1, 8, 27.
Right, and the shadow transform, well, that's a more advanced concept, linking sequences.
Too much for today.
Probably. But the gist is it suggests a structured relationship, how the perfect cubes themselves influence the count of these cube roots of 0 mod n. It's not just random.
Okay, let's stick to the definition then. Examples usually help. It says A4 equals 2. Why?
Okay, let's check mod 4. We look at XO 1, 2, 3.
Right.
So 0 cubed is 0. That's one solution.
Yep.
1 cubed is 1, not 0 mod 4.
Yeah.
2 cubed is 8, and 8 is congruent to 0 mod 4, so EPS2 is another solution.
Ah, there's a second one.
And 3 cubed is 27, which is 3 mod 4.
Not
that.
So just x is 0 and x2, that gives us 4, 2. Makes sense.
Okay.
What about the next interesting one? Maybe a 9. The sequence says A9.
Right, modulo 9. Let's see. X0 gives 0 cubed is 0. That's 1.
Always counts.
1 cubed is 1, 2 cubed is 8. Neither are 0 mod 9.
Okay.
3 cubed is 27. And 27 is exactly 3 times 9, so 27 is 0 mod 9. That's solution number 2 by 3.
Got it.
Then 4 cubed is 64. That's 1 mod 9. 5 cubed is 125, which is 8 mod 9.
Still no.
But 6 cubed, that's 216. Is that divisible by 9? Let's see, 2 plus 1 plus 6 is 9. Yes, it is. So 6 cubed is 0 mod 9. That's our third solution, x6.
Okay, so 0, 3, and 6.
And you can check 7 and 8. They won't work. 7 cubed is 1 mod 9. 8 cubed is 8 mod 9.
So 3 solutions. A9 is 3. Great. These examples really nail down what we're counting.
They do. They show the process.
Now, on to the properties. The OEIS entry says the sequence is multiplicative. That sounds important.
Oh, it's very important in number theory. It means if you have two numbers, say m and n, that don't share any common factors besides 1.
Like 4 and 9.
Exactly. They're relatively prime. Then the value of this sequence for their product, am times n, is just the product of their individual values, am times an.
So A36 should be A4 times A9.
Let's check. We found a 4, 2, and 9 equals 3. So A4 times A9 is 2 times 3, which is 6.
And is A36 equal to 6? We'd need the formula for that.
We would, or we could list the solutions. But yes, multiplicativity tells us A36 should be 6. And the reason this property is so powerful is that it means we really only need to understand the sequence for prime powers, numbers like p to the e.
Ah, because any number n can be broken down into its prime factorization.
Precisely. If you know a for all primes p and exponents e, you can find a n for any n just by multiplying the values for its prime power factors.
And conveniently, there is a formula for AP. It says AP equals p raised to the power of floor of 2e divided by 3.
That's the one, p to the floor of 2e over 3.
So let's use that for our examples. For A4n is 4, which is 2 squared, so P2E2.
Right, so the formula gives 2 raised to the power of floor of 2 times 2 divided by 3. That's floor of 43.
Floor of 43 is just 1.
So 2 to the power 1, which is 2. And that matches what we found, A4x2.
Perfect. And for A9, any 9 is 3 squared, so P3E2.
Same calculation structure. 3 raised to the power of floor of 2 times 2 over 3. Floor of 43 again.
Still 1.
So 3 to the power 1, which is 3. And that matches A9 equals 3.
Brilliant. That formula seems incredibly useful.
It's the core computational tool for this sequence, really. It directly connects the number of solutions to the prime factorization of n.
Okay, there's another formula mentioned too, AN, AC01955N. And A019555 is the largest cube-free divisor of n. What's the connection there?
Right. Cube-free meaning it's not divisible by any perfect cube other than 1.
Got it.
Think about n. You can always write n as a product of its largest cube-free part, let's call it Cn, and some perfect cubes, say k cubed. So n needs 3n k3.
Okay. Like 24 is 3 times 8, which is 3 times 2 cubed. So C24, 3.
Exactly. Or 72 is 9 times 8. Here, C72 would be 9, because 9 isn't divisible by 8 or 27. And 72 equals 923. Ah, wait. 72 equals 8, 9, so it's 923, C72. Let me recheck. 72 equals 23, 32. The cube-free part has primes only to the power 1 or 2. So it's 32 x 9. Yes, C72, 9.
Right. So A01955572 equals 9.
Now, think about the condition x cubed congruent to 0 mod n. This means x cubed must be divisible by n.
Okay.
If n equals Cn k3, then x cubed must be divisible by Cn and by k3. For by 3 to be divisible by k3, x must be divisible by k.
Makes sense.
And for by 3 to be divisible by Cn, well, Cn only has prime factors to the first or second power. If p divides Cn, then by 3 divisible of p squared means x must also be divisible by p.
So basically, x has to be divisible by k and also by every prime factor of Cn.
Correct, which means x must be divisible by the product of k and all the distinct prime factors of Cn. Let's call the product of the distinct prime factors of Cn as rad Cn. So x must be a multiple of k rad Cn.
That sounds a bit different from NCN. Is there a simpler way to see it?
Let's reconsider the condition by 3 equals 0 mod p. For this to hold, x must be divisible by p raised to the power seal, e3.
The ceiling function. Smallest integer greater than or equal to.
Yes. So if n is the product of pi to the e, then x must be divisible by the product of pi to the seal, ei3. Let this divisor be d. The number of multiples of d up to n1 is nd.
Okay, so an equals d, where d is the product of pi to the seal, ai3. How does d relate to the largest cube-free divisor, A019555n?
Let's think about the formula. AP equals P floor 2E3. We also have N product pi and AN product pi floor 2EI3. Now consider NAN, that's product pi floor 2EI3, product pi F floor 2EI3.
Okay, what is EI minus floor 2I3?
Let's test values of EI mod 3. If EI3K, the exponent is 3K floor 6K3, 3K plus 1, it's 3K plus 1 floor, 6K plus 2, 3, the equals 3K plus 1, 2K plus 1. If EI3K plus 2, it's 3K plus 2 floor, 6K plus 4, 3, 3K plus 2, we've got 2K plus 1, K plus 1.
So the exponent is K if EI3K, and k plus 1 if EI3K plus 1 or EI3K plus 2.
Now, what about the largest cube-free divisor, A019555? Let's call it Cn. It's the product of pi raised to the power ei, where ei is I mod 3, but with 0 replaced by 3 if e is a multiple of 3. No, that's not right. Cube-free means the exponents are 1 or 2.
Right, so if n product pi, then Cn product pi ei, where ei equals 1 if ei mod 3 is 1, and ei2 if I mod 3 is 2, and ei0 if e mod 3 is 0. Wait, no, that's cube-free part. The largest cube-free divisor is different. Let's look at the OEIS definition for A019555.
Good idea. A019555n is defined as n largest cube dividing n, or equivalently product pi, where I is the exponent of pi n, reduce modulo 3, 1, 2, 1, 2 to reduce, no. A019555n is product pi ei mod 3 if we map 0 mod 3 to 0, no.
Let's take n72 as 2332. The largest cube dividing n is 23 equals 8. So A01955572 equals 9.
Okay, so Cn AR-phi3, where K3 is the largest cube dividing n.
Right, so C and n contains prime factors pi only to powers 1 or 2.
Got it. Now let's look again at the exponent ni floor 2 ei3. We found it was k if ei3k, k plus 1 if ei3k plus 1, k plus 1 if ei3k plus 2.
And the exponent of pi in Cn, E019555n, that's ei mod 3. Unless I is 0 mod 3, then the exponent is 0. Let's test 72 is 4332. C72, 9 through 2. Exponent of 2 is 0. Exponent of 3 is 2.
Okay, for P2, I3, I mod 3 is 0. Exponent in Cn is 0. For P3, EI2, I mod 3 is 2. Exponent in Cn is 2. So Cn mod pi, ei mod 3, but 0 maps to 0.
Let's try N24, 2331. Largest cube is 238. C24, 2483. For P2, EI3, I mod 3 is 0. Thus 0. For P3, I1, I mod 3 1. XP is 1. So Cn 3 1. Seems Cn radic pi e mod 3, unless I mod 3 is 0, then exponent is 0.
Now compare the exponent I floor 2i3 with the exponent of pi in Cm.
Case ID k, first is k, second is 0, don't match.
Okay, let's rethink. The formula AN and A019555n must be correct if it's in OEIS. Let's check it. For N422, A42, A019554, largest cube dividing 4 is 1, so A019555, formula gives 444, doesn't work. A42.
Oh. Maybe A019555 isn't the largest cube-free divisor. Let's reread the A0189 entry carefully. AN A019555 thing where A09555n is the largest cube-free number dividing n. No, it says largest cube-free divisor. Okay, let's check A019555 itself. It's defined as smallest positive integer m such that m is a perfect cube.
That's different.
That is very different. Okay, so A019555N should be a cube. Let N is product pi. We need M such that MN's product pi plus phi is a cube. This means each I plus phi must be a multiple of 3.
To make I plus phi a multiple of 3, we need phi to be 0 if it is multiple of 3, 2 if I mod 3 is 1, and 1 if I mod 3 is 2. We want the smallest m, so phi should be 0, 1, or 2.
Right, so M A019555N product p phi where phi meter I mod 3 using modulo arithmetic where the result is 0, 1, or 2.
Okay, let's try N42.2, A12N assume mod 3 is 1 mod 3, so A019555N gives A4F42 and R42 matches.
Excellent. Let's try N932E12. F1 on these 2 mod 3 kills 1. A019559 31 kills 3. Formula gives A93 matches again. How about N823 E13 F1 is 3 mod 3 VOS 3 01955 8 or 1 formula gives 8 1 equals 8. Let's check the sequence. 1 through AU so 114 doesn't match.
There must be something subtle. Let's reread the formula in A000189. It says formula AN, AEE is A019555, N RJ Mithar, OG 16 2010. Maybe this formula isn't universally correct, or there's a condition. Let's trust the prime power formula, AP, P floor 2E3.
Okay, using that, A8, A23, here P2E3, formula gives 2 floor 2 through 2 equals 2E2 floor. That does match the sequence term.
Good. So the prime power formula seems reliable. Let's stick with that one. The connection to A019555 might be more nuanced or perhaps even incorrect as stated. It happens sometimes in collaborative resources like OEIS, though usually gets corrected.
Okay, prime power formula it is. Now, about these Dirichlet generating functions, the first one mentioned is zeta, 3s to 2, times a product over primes. What can we glean from that?
Well, Dirichlet generating functions, DGFs, are series like some AMNS. They encode the sequence. The fact that it involves the Riemann zeta function, ZRS, often points to deep arithmetic properties.
And the product form.
That Euler product form, the product over primes, is directly related to the sequence being multiplicative. Each factor in the product usually corresponds to the contribution from powers of a single prime p. The specific form zeta 3s2 product, 1 plus 1p is plus 1p2 s1, connects the sequence's behavior across all primes.
And the second, more complex DGF from Vaclav-Kosovac.
That likely arises from a different manipulation or might be better suited for, say, asymptotic analysis, figuring out how the sequence behaves on average or for large n. Different forms can highlight different aspects.
Speaking of asymptotics, there's that formula for the sum. Sum AK, for k1 to n, is approximately something involving n, log n squared, and log n.
Right. Sum AK grows roughly like F1n12 log n2. The key thing is the n log n2 growth.
Faster than linear, but not quite quadratic.
Exactly. It tells you the solutions di3 mod k aren't that rare on average. The density kind of increases slowly. The other constants involved, like gamma, Euler-Mascheroni, and details about that function fs at s1, just refine the estimate.
It shows how even this simple congruence connects to some pretty advanced analytic number theory.
It really does. The tools needed to get that asymptotic formula are non-trivial.
Okay, let's switch gears to computation, the Mathematica code. Array function n, count array power mod, hashtag 3n and nn, 0000000.
Right.
This looks like it just does it directly.
Yeah, that's a direct implementation of the definition. For each n, it makes a list of 03 mod n, 13 mod n, up to n13 mod n, and then just counts how many zeros are in that list.
Simple, but maybe slow for big N.
Definitely. Calculating n cubes and checking them gets slow.
In the Perry code, an, my factor n, prod I1, hashtag FU151253. This looks different.
This uses the prime power formula we liked. First factor n gets the prime factorization, like P1, E1, P2, E2.
Okay.
And it loops through this factorization. For each prime phi, 1, which is pi, and exponent phi, 2, which is I, it calculates pi raised to the power floor 2ii3. The 3 likely means integer division by 3, giving the floor.
And prod multiplies these results together for all prime factors.
Exactly. This leverages the multiplicativity and the prime power formula. Much, much faster for large n.
Makes sense. And the Dirichlet code in Perry.
That would likely compute the sequence terms using the Dirichlet series representation, perhaps by expanding the Euler product. Another way to generate terms, especially useful if you already have tools for DGFs.
Okay. We've mentioned the connections to A000578 cubes and A019555 related to making Hamacube. The context links in OEIS are always great for digging deeper.
Absolutely essential. It positions the sequence within the whole landscape of number theory.
The keywords, non-mult, easy. Easy seems debatable now.
Well, the definition is easy to state and understand. The consequences and analysis, maybe less so, but compared to some sequences, it's relatively accessible.
Fair enough. And authored by Neil Sloan himself, updated recently. It's clearly a well-regarded sequence.
A fundamental one, I'd say.
Now, crucially, the OEIS entry points to a paper, Squares and Cubes Modulo N, by Finch and Siwa. It sounds like this paper tackled our sequence head-on.
Yes, that paper is a key reference for this kind of problem. They look at solutions to xk congruent to a mod n for various k and a, including our case, k3 equals 0.
And it mentions section 1.7, cube roots of nullity, directly relates to A000189.
Right, nullity referring to being congruent to 0. That section likely derives the prime power formula APR equals P floor to R3 and discusses the Dirichlet series.
The OEIS also notes the paper gives asymptotic results, like the sum growing, like Cn ln n2.
Yes, they likely use methods like the Selberg-Delange method, powerful techniques for estimating sums related to multiplicative functions to get those precise asymptotic formulas, including the constant c.
So that paper provides the rigorous underpinning for a lot of what's summarized in the OEIS entry.
Precisely. The OEIS is the index and summary. The reference papers often contain the full proofs and derivations.
Okay, so wrapping up our dive into A00189, we started with a simple question. How many numbers x from the 0 to n1 have x cubed being 0 modulo n?
And we found the answer lies in the prime factorization of n, captured beautifully by the formula AP equal P floor 2E3.
We saw it's multiplicative, which simplifies things immensely. And it connects, albeit maybe confusingly via A019555, to the cubic structure of n.
And leads into deeper waters with Dirichlet generating functions and asymptotic estimates that describe its average behavior.
It really shows the power of the OEIS as a launchpad, doesn't it?
Absolutely. A starting point for exploring these rich mathematical ideas.
For number theory students listening, some paths forward could be try deriving that prime power formula yourself. It's a good exercise in modular arithmetic.
Definitely. Or investigate the connection with A019555 more deeply. Maybe clarify that formula, explore the DGFs.
And maybe look at the Finch and Siwa paper to see those analytic techniques in action. Or even generalize, what about solutions to by 4 is equal 0 mod n, or xk?
Excellent suggestions. How does the exponent k change the picture? That's a great question.
So a final thought to leave everyone with. Understanding polynomial congruences, like this by 3 euro mod n, is really fundamental. It seems basic, but it's a thread that runs through so much of number theory, from basic properties to cryptography and beyond.
Well said. Simple questions, deep connections, that's the beauty of it.
Thank you for joining us on this deep dive.